Double replacement reactions. Now, what you need to know about these, this is our other type of reaction where we'll have to predict products. It's really an exchange of ions between two different compounds. So if you see two compounds on the left, you're most likely dealing with a double replacement reaction. These are different rules than single replacement reactions. So for the double replacement, don't worry about activity series. Don't worry about the activity series of metals. Don't worry about the activity series of the halides. This is a different set of rules. These are not redox reactions. No one is giving electrons from one compound to another. What we see in double replacement reactions possibly are precipitates forming. In this particular case, we have sodium sulfide, which is aqueous, it's dissolved in water. Cadmium 2 nitrate, which is also dissolved in water. We make cadmium 2 sulfide, which is a solid. It is insoluble in water, so it precipitates out. And sodium nitrate, which is a aqueous compound. Nitrates all dissolve in water. There are no exceptions to that. Another possibility, not quite as common, as you might see a gas bubbling out of solution. In this particular case, we have sodium cyanide, sulfuric acid becoming hydrogen cyanide, which is a gas, and sodium sulfate, which remains in an aqueous form. As I've mentioned during class and in the previous video on double replacement reactions, this is what they use in the gas chamber. It's a very deadly gas. One more type of double replacement reaction is where we take a component of water, the hydrogen ion, and we add it to the hydroxide ion, which is the other component of water. We put it together to form a water molecule, and then an aqueous solution. Now, this one would be harder to see. You'd have two solutions. You're making water in a solution. Very hard to see. But what you would see is some sort of a temperature change. So in the first reaction, we do see a precipitate forming, our solid cadmium 2 sulfide. Second one, we have a gas bubbling out, our hydrogen cyanide. And in the third one, while we don't see anything precipitating or becoming a gas, this would actually cause a change in the heat of the overall system. Some water formation reactions are exothermic, some are endothermic. Sometimes the temperature goes up, sometimes the temperature goes down. But in any case, you will see a change in temperature, which is a definite sign of a chemical reaction. Now, what you'll need to do on the quiz is predict a precipitate, which is based on the solubility rules. Now, there are many different versions of a solubility table. You should get used to seeing many different varieties. What you need to know, nitrates are soluble. Acetate, C2H3O2 with a minus charge, are mostly soluble, although silver acetate is not entirely soluble. These are your halides: chloride, bromide, iodide. They are all soluble except silver chloride. This should be lead 2, but lead 2 chloride and mercury, this is actually mercury 1 chlorides. Lead 2 chloride is slightly soluble in cold water, but moderately soluble in hot water. This is missing a letter here, but it's not very soluble. Sulfates are generally soluble except for barium sulfate, lead 2 sulfate, calcium sulfate, which is plaster of Paris, and strontium sulfate. Carbonates, phosphates, generally insoluble except for sodium, potassium, and ammonium. Hydroxides are generally insoluble except for sodium, potassium. Barium hydroxide, calcium hydroxide will dissolve a little bit in water, but not tremendously. Sulfides are insoluble with very few exceptions. Sodium, potassium, ammonium are all the real exceptions. The magnesium, calcium, strontium, barium, these will also occasionally dissolve. Actually, they will dissolve in water, soluble. My mistake. Aluminum and chromium 3 will react with water and become the hydroxide. But that's not something that we will have to worry about at this moment. In general, all sodium salts, potassium salts, and ammonium salts are soluble in water. Very few exceptions for that. As I wanted to point out again, Cl, Bri, these are what we call the halides. Get used to hearing halides. Halides are group 17, fluorine, chlorine,
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118,
So what you will need to do with double replacement reactions is predict products. We will have two ionic compounds in an aqueous solution. If they are dissolved in water, they are dissolved as ions. All ionic compounds are ions in solution, which means they are either a monoatomic ion or a polyatomic ion. Most cations are monoatomic with the exception of ammonium. Most of the polyatomic anions are negatively charged. If they have oxygens, they end in ate. Unless they have one less oxygen, then it's ite. And the monoatomic anions end in ide: chloride, fluoride, oxide, phosphide, nitride. So in this particular case, we have silver nitrate and potassium chromate. Now, chromate was not on the table that I showed you earlier, but chromates are generally insoluble in water, which would mean in my solution, I have 2 formula units of silver nitrate, which means 2 silver ions floating around and 2 nitrate ions floating around. I would also have potassium chromate. So the exception to the chromates being soluble are the group 1 elements, sodium, potassium, particularly. We would have 2 potassiums floating around. That's a misprint. I should have the plus up there. And then 2 chromates. Chromate has a -2 charge. When they are put together, silver chromate is not soluble in water. So as soon as one of these silvers finds the chromate and another silver finds the chromate, it precipitates out of the solution. This should actually, let me fix this. This should be Ag. This should be silver chromate with a... Oops, okay. Just make sure we see that that needs to be fixed. I don't want to forget about that and leave it not fixed for later. So silver chromate, where we were. Silver chromate. So one silver will find the chromate, another silver will find the chromate, because this has a plus, each one of these has a +1 charge, a -2 is needed to balance the +2s. So just think of it this way. This plus charge is going to be attracted to a minus charge. It's going to come over and stick to it. Still has a -1 charge, so another one will come and stick to it. And that's when it precipitates out of the solution. And in the solution, what remains is the potassium ions and the nitrate ions, because all nitrates are soluble in water. The next one would be sodium sulfate and barium chloride. Now what you have there is 2 sodium ions. They will break off of sodium sulfate. You have the 1 sulfate with a -2 charge. They will separate in an aqueous solution. You have barium, which also separates from 2 chlorides. Do not think of this as one unit. These are 2 separate chloride ions. Do not keep these together. It just means that 2 is just a convenience to tell me there are 2 chloride ions. There is no polyatomic anion where you have a Cl2 staying together. It would be 2 chlorides. From there, barium sulfate, because sulfates of barium are insoluble, as we saw in our table on the previous slide, barium sulfate precipitates out of solution. Most barium salts are highly, highly toxic. Barium sulfate, because it is not soluble in water, is not particularly toxic. In fact, they use barium sulfate if you need to have imaging of your digestive system. You will actually drink a solution of barium sulfate, which is opaque to X-rays. It will absorb the X-rays, so you can actually make a very nice image of your digestive system as you coat the inside of your system with barium sulfate, which doesn't taste very good. It's a very chalky, plastery kind of a taste, but it would be excellent for the medical need for imaging your digestive system. The other thing that we have here, we have 2 sodium chlorides. So these 2 sodiums broke off. They broke off independently. These 2 chlorides broke off independently. If we were to look at the solution, we would still see 2 sodiums floating around, 2 chlorides floating around. These did not actually come together. This is just a matter of convenience to say that if we poured off the liquid, we would have sodium chloride dissolved in the water. And if we evaporated the water, then we would actually we'd see salt crystals, sodium chloride crystals coming together. One additional example, lithium hydroxide, sodium chromate. Now we know that the group 1s, which include sodium and lithium, their hydroxides are soluble and their chromates are soluble, which they will dissolve in water. So what we would have on one side are my 2 lithium ions floating, my 2 hydroxides in solution, my 2 sodium ions in solution, and my chromate in solution. But what that would really mean, hydroxides, whether they are lithium hydroxide or sodium hydroxide, they still dissolve in water. My sodium chromate and my lithium chromate also dissolve in water. So what do I have? I just have a big jumble of ions. In fact, this mixture of ions that I have here is exactly the same as the mixture of ions on the other side. I would see no visible reaction in this particular case. Now, an important series of double replacement reactions are the acid-base reactions. Here is one acid. It's hydrogen sulfate when it's not dissolved in water. It's an oily liquid at room temperature, but when you dissolve it in water, it becomes sulfuric acid. If I put sulfuric acid with sodium hydroxide dissolved in water, I make sodium sulfate and I make water. This would be an exothermic reaction. The temperature of the system would increase. So that's my evidence of a chemical reaction. Even though I have 2 solutions here and I have a solution of sodium sulfate and just extra water in my solution, I would see no precipitate and I would see no gas bubbling out. As any compound, ionic compound dissolves in water, I end up getting ions. So here I get 2 from the H2, I get 2 hydrogen ions. The hydrogens do not stick together. They're 2 independent hydrogen ions that break away from the sulfate. I have a sodium that breaks away from a hydroxide, and because I have 2 formula units of sodium hydroxide, I get 2 units of sodium ions and 2 units of hydroxide ions. When they dissolve in water, I actually need to fix this because sodium sulfate is aqueous. So that's a misleading reaction. So what do I have? I have sodium sulfate still dissolved in water, and I have water, extra water being made. So if you notice, I have 2 sodiums over here, 2 sodiums over here, 1 sulfate here, 1 sulfate here. They did not do anything in this reaction. We call them spectator ions. Nothing happened between the sodiums on one side and the sodiums on the other, the sulfates on one side, the sulfates on the other. The important part of the reaction was that 2 hydrogens with a plus charge were finding 2 hydroxides with a minus charge. A plus and a minus canceled each other out. I ended up with 2 molecules of water. To put it more simply, we had a hydrogen ion finding a hydroxide ion and becoming water. This is a neutralization reaction. We will see more about this coming up in future units. This mixture would get warmer. That would be my sign of a chemical reaction. Now, one other thing we need to focus on for double replacement reactions are the net ionic equations. That's where we look at what is truly important in the reaction. Now, iron 2 sulfate dissolves in water. Sodium carbonate dissolves in water. But most carbonates, in this example, iron 2 carbonate, is insoluble in water, whereas most sulfates are soluble in water. So the important thing is that we would see a precipitate forming. That precipitate came from 2 ions on the left side, 2 in the reactants. So remember, these 2 are dissolved originally in water. So I have iron 2 ion dissolved in water. I have sulfate ion dissolved in water. I have 2 sodium ions dissolved in water. I have a carbonate ion dissolved in water because though most carbonates are insoluble in water, sodium carbonate, the group 1 carbonates, are soluble in water. However, if we go to group 2, something like calcium carbonate is not soluble in water. And what am I forming? I'm forming the lead 2 ion finds the carbonate and becomes lead 2 carbonate. Sodium ion on the left, sulfate ion on the left, and on the right, they don't actually have any changes. So as we saw earlier, the sodium and the sulfate are not doing anything in this reaction. They are what we call spectator ions. They sit back and let the reaction take place, but they don't actually participate. What actually changes is we have an iron 2 ion and a carbonate ion coming together to form iron 2 carbonate. I think I might have kept saying lead. This is iron. Iron 2 plus carbonate makes iron 2 carbonate. This is the net ionic equation. The spectator ions have been removed in this case. Lead 2, I keep saying lead 2. Iron 2, carbonate, and then iron 2 carbonate. The spectator ions are removed from this equation. Let me get my computer plugged in very quickly. Okay. One more example of an ionic equation. Now, again, you have to be clear what you're looking at here. Aluminum chloride is dissolved in water. Silver nitrate is dissolved in water. They're dissolved as ions. So, our halides, such as aluminum chloride, are soluble in water. Nitrates are all soluble in water. So these two should be dissolved in water. Now look at chlorides, the exception. Chlorides are soluble except silver chloride. So this is my precipitate. Aluminum nitrate, again, all nitrates are soluble. To look at this another way, just so we don't get confused, I have an aluminum 3 ion floating around. These are chlorides, 3 separate chlorides that come out of a formula unit of aluminum chloride. They are in no way connected together. Don't do anything with Cl3 when it dissociates into its ions. These are 3 separate chlorides. I have 3 formula units of silver nitrate, which means I have 3 silver ions, and I have 3 nitrate ions. When they come together, 1 silver will find 1 chloride. That will happen 3 times because I have 3 silvers and 3 chlorides. The plus charge and the minus charge, I will make 3 formula units of silver nitrate. The aluminum actually remains aluminum 3 ion, and the nitrate remains nitrates. This is still dissolved in water. They remain in their ion forms. So again, these are the spectator ions. They did nothing from one side of the equation to the other. The precipitate is silver chloride. That came from silver, 3 of them, finding 3 chlorides. Though we could simplify the net ionic equation, notice the ratio is 3 to 3 to 3. That's the same thing as 1 to 1 to 1. So 1 silver ion finds 1 chloride ion and becomes silver chloride. That is my net ionic equation. Now, another reaction. I'll have to remove that or fix that animation. But we have hydrogen chloride, which dissolved in water as hydrochloric acid. Adding it to sodium hydrogen carbonate, also known as baking soda or sodium bicarbonate, becomes sodium chloride dissolved in water. So I'm actually still dealing with sodium and chloride ions. Water's forming. And here I have evidence of a chemical reaction. I have a gas coming out. What it actually looks like is hydrogen ion, chloride ion, sodium ion, bicarbonate ion or hydrogen carbonate ion, sodium ion, chloride ion, and then water and carbon dioxide. Spectator ions are sodium, because sodium appears on both sides exactly the same, and chloride, which appears at the same on both sides. The net ionic equation, this is a little bit more complicated, but it would be my hydrogen ion, which actually does something, my hydrogen carbonate anion, which actually does something, and forming water and carbon dioxide. With that, it's a nice overview of double replacement reactions, and be prepared to be quizzed on them very soon.